Find the average rate of change of r of x equals 1 over 1 minus x on the interval from a to a plus h. At this point, hopefully, you're comfortable with the process. The average rate of change we're going to calculate by taking r of a plus h minus r of a all over h. When we substitute in a plus h and a for our function, this gives us 1 over 1 minus the quantity a plus h minus 1 over 1 minus a all over h. Now here, we're going to have to distribute this subtraction to get rid of those parentheses. So we can rewrite this as 1 over 1 minus a minus h minus 1 over 1 minus a all over h. That is a lot of subtraction signs, so we need to be careful. Again, we're going to have to multiply by the LCD. In this case, the LCD is 1 minus a minus h times 1 minus a. And so we're also going to multiply the bottom by that. And just like all the other problems, we will be distributing up in the top. Now, when we do this, in the first fraction, the 1 minus a minus h's cancel, and we're left with 1 times 1 minus a, which is 1 minus a. Then we are subtracting what we get when we multiply the second one. Here, the 1 minus a's cancel, and we're left with 1 times 1 minus a minus h, which is going to be 1 minus a minus h. Of course, that will go in parentheses because that whole quantity needs to be subtracted. Then in the bottom, we'll have h times 1 minus a minus h times 1 minus a. In the top, we're going to distribute that subtraction. This gives us 1 minus a minus 1 plus a plus h all over h times 1 minus a minus h times 1 minus a. We can cancel the 1's and the a's. This leaves us with h over h times 1 minus a minus h times 1 minus a. And at this point, we can cancel out the h's because those are common factors in the top and bottom. And when we do that, that leaves us with 1 in the top because h is the same as h times 1. And so this leaves us finally with 1 over 1 minus a minus h times 1 minus a. And this is our final answer. I want to do one more thing here. I want to give you just a little bit of a vision of where this is going to go in calculus. Now, I need to preface this by saying that what I'm doing here is a gross oversimplification. There is so much going on in calculus, and I am technically doing something wrong here because I'm simplifying stuff more than it should be. But in calculus, instead of looking at the average rate of change, we want to know the instantaneous rate of change. So if we have a graph, for example, instead of looking at the average rate of change between two different points, so we'd be looking on an interval between a and a plus h, for example, we want to know the instantaneous rate of change. That's difficult for most people to understand right away, but it's easier to understand if we think about speeds. Remember that we were looking for average rate of change because in the very beginning we were looking for the average speed. Well, the instantaneous rate of change in that situation would be the instantaneous speed. Not the average speed over an interval, but the speed exactly at a certain moment in time. To do that, effectively, we're looking at a single point. So instead of looking at an interval of length h, we're looking at an interval of length 0. Now, there's so much more that goes on here. We spend weeks and weeks and weeks on this in calculus. But effectively, we want to look at what happens when the width of our interval, which is h, ends up being 0. Now, if h equals 0, and we don't actually do this in calculus, we look at a thing called a limit, but I want to do this in 3 minutes or less, so I'm just going to oversimplify everything. If we're looking at a point instead of an interval with width, so we've got no width and h is 0, then in this situation, when h is 0, we end up with 1 over, and 1 minus a minus h just becomes 1 minus a. And so we've got 1 minus a times 1 minus a, which is 1 minus a quantity squared. And this more or less gives us the instantaneous rate of change at x equals a. Now again, I know I've said this multiple times, this is a gross oversimplification. There is so much going on here. We can't actually just plug in 0 for h for certain situations. We have to be looking at something much more complicated called a limit. There's so much going on. But in the end, this ends up being very useful because it gives us an expression that represents the instantaneous rate of change for any x value in the domain. And that's very useful because we might want to know the instantaneous rate of change for 8 different points, or if we're looking at speeds, we might want to know the instantaneous speed at any given moment. And here we can just plug in any value for a, and that will give us the instantaneous rate of change at that moment. So again, all of this is just a little bit of a glance, a glimpse at what's going to happen in calculus. But I just wanted to show you why these things are so important and useful. Because right now we've just been going through and we've gotten a complicated answer that we didn't really do anything with. But in calculus, you are absolutely going to be doing much, much more with all of this.